relatively more difficult result, which are called propositions. Now a theorem has to be quite important. A theorem about some object or about some class of mathematical objects tells you something definite and important about that object. That comes from not necessarily proposition, but from both lemmas and propositions. Although in some theorems you may see just a proof is carried out without ever using any lemma or proposition, that is also possible. And a corollary is an easily derivable special case of a theorem or proposition or even lemma. Okay, so these are the words that are used to show how important a result in mathematics is. Okay, so that was a quick digression. Now we come back to where we were. So we have seen why vacuously true statements are needed. Okay, now more about implication. So you are given an implication where the hypothesis is X and conclusion is Y. Now, given such an implication, you can define its converse and contrapositive. These are statements associated to an implication like this. The converse of this implication is the statement Y implies X. Okay, and the contrapositive of X implies Y. This is a little bit, it looks more difficult, but we will see what it means. The contrapositive of X implies Y is the statement negation of Y implies negation of X. Okay. So these are two statements associated with an implication. Now let's look at an example. Let X be a real number with this condition. You look at this statement: X is equal to 2 implies X squared is equal to 4. This is an implication where the hypothesis is X is equal to 2 and this is the conclusion, X squared is equal to 4. Now what is its converse? To form the converse, you just interchange the hypothesis and conclusion. So now conclusion becomes hypothesis and hypothesis becomes conclusion. This is the converse. Okay. Now, what about the original statement? What about the original implication? It is true, right? When X is equal to 2, then X squared is equal to 4. 2 squared is 4. So this is true. What about the converse? Is the converse true? No, because if X squared is 4, it's not necessarily true that X is equal to 2. Because you also have minus 2 squared is equal to 4. So X can be minus 2 also. So in this case the converse is false. Okay, so if an implication is true, the converse may not be true. It is false. However, it may not be false also. That's also not always the case. You look at this example. Under the same condition that x is a real number, you look at this statement. X is equal to 1 implies x cube is equal to 1. This is our statement, our implication. What is its converse? What is its converse? Its converse is x cube is equal to 1 implies x is equal to 1. In this case, you see, of course, the statement is true. The first implication is true because when x is 1, 1 cube is equal to 1. Now, but what about the converse in this case? The converse is also true. When x cube is 1, then x has to be equal to 1. Remember that x is a real number. There are two other possibilities which are not real numbers. Okay, two non-real complex values of x are there whose cube is also equal to 1. But since we have decided to choose the variable x to be a real number, we get only one situation.